What if I told you that being the biggest and strongest could actually be your greatest weakness? 2 million years ago, Africa was home to Dinopithecus ingens, a baboon that could reach weights of up to 170 pounds, with males averaging around 100 pounds and standing nearly 5 feet tall when upright. This massive primate had incredibly powerful jaws designed for processing tough foods and the social coordination to fend off saber-toothed cats. Yet despite all these advantages, Dinopithecus went extinct while smaller, weaker baboons survived. The reason why will completely change how you think about survival and evolution. To understand just how massive Dinopithecus ingens really was, consider that a modern Chacma baboon weighs around 60 pounds. Dinopithecus males averaged around 100 pounds, with some reaching up to 170 pounds of solid muscle and bone. Standing when upright, this primate reached heights of nearly 5 feet, making it comparable to a large dog, but with the intelligence and social complexity of a highly evolved primate. The fossil evidence from South African cave sites like Kromdraai, Swartkrans and Sterkfontein reveals a creature built on an entirely different scale than anything we see in the primate world today. The skull of Dinopithecus tells the story of an evolutionary arms race with its environment. The cranium housed a brain proportionally similar to modern baboons, but the facial region expanded dramatically to accommodate massive jaw muscles. The sagittal crest, a bony ridge running along the top of the skull, provides attachment points for temporalis muscles capable of generating tremendous bite forces. The inflated cheekbones created a distinctive dished face appearance, displacing the eye sockets forward and resulting in a weak brow ridge and receding forehead. The mandible itself created space for enlarged molars and premolars designed to process the toughest plant materials. These were not just bigger teeth, they were geological hammers wrapped in enamel. What makes this dental architecture even more remarkable is how it functioned within coordinated social groups. Dinopithecus lived in mixed-sex communities where males and females worked together to defend territories and resources. These groups could present a formidable presence when confronted by threats, with their impressive size and robust anatomy serving as natural deterrents. The fossil record suggests that injuries from encounters with large predators were relatively rare, indicating that their physical presence and group coordination provided effective protection in the competitive landscape of the Pleistocene. The body plan that supported this massive frame was engineered for terrestrial life across varied woodland terrain. Unlike modern baboons that spend considerable time in trees, Dinopithecus was built as a ground-dwelling quadruped. The limb bones show robust construction within large muscle attachment sites, particularly in the hindquarters, where powerful gluteal muscles provide propulsion across uneven surfaces. The hands retained the dexterity necessary for food manipulation, but the overall structure prioritized weight-bearing over climbing agility. This terrestrial specialization allowed Dinopithecus to exploit niches unavailable to more arboreal primates. The ecological conditions that favored such gigantism were unique to the Pleistocene period in Africa. During this time, Dinopithecus shared its environment with other large primates and early hominins, creating a competitive landscape where size provided distinct advantages. Abundant, high-energy food sources in woodland margins provided the caloric foundation necessary to support massive bodies. The climate remained relatively stable, with predictable seasonal patterns that allowed large-bodied animals to plan their foraging strategies around reliable resource availability. These factors created an evolutionary sweet spot, where being bigger provided clear advantages without overwhelming costs. However, this specialization came with a hidden vulnerability that would prove fatal. While smaller baboons adapted to life on the expanding savannas, Dinopithecus remained committed to woodland margin habitats. These environments provided the specific combination of underground storage organs, fallen fruits, and occasional animal protein that could satisfy their enormous caloric requirements. The giant baboons developed feeding behaviors and social structures specifically adapted to these marginal zones between dense forest and open grassland. The massive jaws that made Dinopithecus so formidable also revealed the constraints of its lifestyle. Every aspect of their anatomy was calibrated for processing high-energy foods that required significant bite force to access. This specialization made them incredibly efficient within their chosen niche, but also created a dependency that would become problematic as environments changed. The very adaptations that made Dinopithecus successful also made them prisoners of their own extraordinary energy demands. The metabolic demands of such a massive primate created an energy crisis that would define every aspect of Dinopithecus behavior. While modern baboons require substantial daily caloric intake, Dinopithecus needed dramatically more energy to maintain their massive frame and support their active lifestyle. This represented a significantly higher energy intake than their smaller relatives, forcing them into a constant search for the most calorie-dense foods available in their environment. The sheer mathematics of survival meant that every waking hour revolved around locating, processing, and consuming enough food to fuel their enormous bodies. Their dietary strategy focused on an omnivorous approach that included underground storage organs, thick-rooted tubers, energy-rich fruits found along woodland margins, and likely honey and termites when available. These foods contained concentrated starches and sugars that could provide the caloric density necessary to sustain such large bodies. Unlike smaller baboons that could supplement their diet with leaves, shoots, and other readily available vegetation, Dinopithecus required foods that delivered maximum energy per bite. Their powerful jaws became specialized excavation tools capable of unearthing buried roots and crushing through tough outer layers to access the nutrient-rich cores within. The time constraints imposed by these feeding requirements created serious limitations on group dynamics and territorial range. Evidence from South African cave deposits suggests that Dinopithecus groups were smaller than those of contemporary baboon species, likely because large aggregations would have depleted local food resources too quickly. Individual animals spent extensive periods engaged in active foraging, leaving limited time for social interaction, grooming, or territorial defense. The extended feeding schedule also restricted daily travel distances, as groups needed to remain within range of productive foraging areas throughout the daylight hours. Their dental adaptations reveal the mechanical challenges of processing such specialized foods. The enlarged premolars and molars featured thick enamel ridges designed to grind through fibrous root material without wearing down quickly. The temporomandibular joint, where the jaw connects to the skull, developed enhanced leverage that could generate tremendous crushing forces. When animal protein became available, these same adaptations allowed Dinopithecus to crack open bones and access calorie-rich marrow that smaller primates could never reach. The entire chewing apparatus represented millions of years of evolutionary refinement toward maximum food processing efficiency. Seasonal variations in food availability created additional stress on these energy-intensive lifestyles. During dry periods, underground storage organs became harder to locate and required deeper excavation, increasing the energy cost of obtaining each meal. Fruit production in woodland margins followed unpredictable cycles, forcing groups to travel greater distances between productive patches. The fossil record indicates that Dinopithecus populations showed clear evidence of seasonal stress, with bone chemistry revealing periods of nutritional strain that coincided with resource scarcity. Social coordination became essential for exploiting scattered high-energy food sources without internal competition that could prove fatal. Groups developed sophisticated communication systems that allowed them to signal the discovery of productive foraging sites while maintaining peaceful coexistence during feeding. The large body size that provided protection from predators also created challenges during resource competition, as aggressive encounters between massive animals could result in serious injuries that would compromise survival. The metabolic trap that Dinopithecus found themselves in became increasingly problematic as environmental conditions grew less predictable. Their massive bodies required consistent access to high-quality food sources, but their specialized diet made them vulnerable to any disruption in resource availability. Unlike generalist feeders that could switch between different food types as circumstances changed, Dinopithecus remained locked into an energy-intensive lifestyle that demanded specific ecological conditions. The stability of their woodland margin habitats would soon face an unprecedented test that would challenge the very foundations of their survival strategy. Around 2 million years ago, Africa began experiencing one of the most dramatic environmental transformations in its geological history. The early Pleistocene period brought fundamental changes to rainfall patterns across the continent, shifting from relatively stable, predictable wet and dry seasons to increasingly erratic precipitation cycles. This climatic upheaval would culminate in the mid-Pleistocene transition, characterized by the continual prolonging of dry cycles that created unprecedented challenges for large-bodied species. These alterations did not happen overnight, but unfolded across several 100,000 years, creating a continental-scale experiment in survival that would determine which species could adapt and which would vanish forever. The woodland margin habitats that Dinopithecus specifically preferred began fragmenting as rainfall became concentrated into shorter, more intense periods, followed by extended droughts. These transitional zones between dense forest and open grassland had provided the perfect combination of resources that giant baboons required, but they proved especially vulnerable to climatic disruption. Forest margins that once provided continuous corridors of food, rich vegetation, broke apart into isolated patches separated by expanding grasslands and semi-arid zones. These fragmented landscapes forced large-bodied primates to travel unprecedented distances between productive foraging areas, turning what had been efficient feeding circuits into exhausting journeys across hostile terrain. Cave deposits from sites like Sterkfontein and Swartkrans preserve detailed records of this climatic upheaval through layers of sediment that accumulated over thousands of years. These South African sites show clear evidence of the environmental changes that directly affected Dinopithecus populations, documenting the shift toward more open environments that occurred 2 million years ago. Isotopic analyses of ancient soils reveal steadily increasing aridity with carbon isotope ratios, indicating a shift from woodland vegetation dominated by trees and shrubs to grassland ecosystems characterized by drought-resistant grasses. Oxygen isotope data from fossil teeth show that seasonal variations in temperature and humidity became more extreme, creating longer dry periods that stressed even the most resilient plant communities. The underground storage organs that formed the dietary foundation for Dinopithecus became increasingly scarce and unpredictable across these transformed landscapes. Root systems that had once spread extensively through moist woodland soils retreated to deeper layers where they required more energy to excavate. Tuber production declined as plants redirected resources towards survival rather than reproduction, leaving fewer high-energy food sources available during critical periods. The reliable seasonal cycles that had allowed large primates to plan their foraging strategies dissolved into unpredictable resource availability that demanded constant adaptation. Resource dispersion created cascading effects throughout primate communities as food patches became scattered across vast distances. Smaller, more adaptable species could exploit marginal habitats by switching between different food sources as opportunities arose, but the massive caloric requirements of Dinopithecus made such flexibility impossible. While smaller primates could survive on scattered fruits, leaves, and insects during lean periods, the giant baboons needed concentrated energy sources that were disappearing from the landscape. Their specialized feeding apparatus, so perfectly adapted for processing high-energy foods, became a liability in environments where such resources were increasingly rare. The fossil record from major South African sites documents dramatic changes in faunal composition during this period. Species adapted to woodland environments either disappeared entirely or retreated to remaining forest refugia, while grassland specialists expanded their ranges across newly available habitats. The megafauna that had dominated Pleistocene ecosystems faced extinction pressures as their large body sizes became unsustainable in resource-scarce environments. Archaeological layers show clear evidence of population crashes among large-bodied species, with fossil abundance declining sharply during periods of maximum environmental stress. As Dinopithecus struggled with these mounting environmental pressures and dwindling food sources, they would soon face an entirely new form of competition that would prove even more decisive than climate change itself. The arrival of early Homo erectus and Homo ergaster, armed with stone tools, marked the beginning of the end for Dinopithecus ingens. These smaller-bodied hominins, weighing less than half of what the giant baboons did, possessed something far more powerful than crushing jaws, the ability to manufacture and use tools systematically. While Dinopithecus relied on brute force to access underground resources, hominins developed Oldowan stone technology that could slice through tough root systems and excavate buried tubers with surgical precision. A simple chopping tool could accomplish in minutes what took a giant baboon hours of exhausting digging and crushing. The archaeological record from sites across eastern and southern Africa reveals the sophistication of early hominin plant processing techniques. Stone tools dating to this period show clear wear patterns consistent with digging and cutting fibrous plant materials. Sharp-edged choppers could sever thick root systems cleanly, while pointed implements functioned as efficient digging sticks for extracting deeply buried storage organs. These tools allowed hominins to access the nutrient-rich cores of roots and tubers without expending the massive amounts of energy that Dinopithecus required for the same task. However, the technological story proves more complex than simple hominin dominance. Evidence from South African cave sites suggests that Dinopithecus may have possessed their own rudimentary tool using capabilities. Bone fragments found in association with giant baboon remains show wear patterns consistent with use as digging implements and food processing tools. These bone tools could have been employed to extract termites from mounds, dig for roots, or process tough plant materials more efficiently than using teeth alone. While less sophisticated than hominin stone technology, these implements suggest that Dinopithecus was not entirely without technological resources in their struggle for survival. The energetic advantages of systematic tool use still created a fundamental shift in competitive balance between these species. A hominin group could systematically strip an area of its underground resources in a fraction of the time it took Dinopithecus to process the same foods, even with their bone implements. Stone tools never tired, never wore down significantly during use, and could be manufactured quickly when replacements were needed. This technological edge allowed smaller-bodied hominins to extract far more calories per unit of energy expended, making them incredibly efficient competitors for the same ecological niche. The temporal overlap between these species, spanning from about 2.27 to 0.87 million years ago, provides compelling evidence for direct competitive pressure during this critical period. Archaeological evidence suggests that early tool users could exploit underground storage organs across much wider geographic areas than giant baboons, who remained constrained by their massive energy requirements and slower processing speeds. The ability to quickly harvest and process high-energy plant foods allowed hominin populations to maintain larger group sizes while covering more extensive territories in search of productive foraging sites. Competition for the same ecological resources created unsustainable pressure on giant baboon populations already stressed by climatic changes and habitat fragmentation. Hominins could harvest critical underground storage organs faster and more completely than their massive competitors, often leaving areas stripped of the high-energy foods that Dinopithecus desperately needed. The systematic exploitation of root and tuber resources by tool-using groups effectively removed the dietary foundation that had supported giant baboons for thousands of years. The irony of this competitive relationship reveals how evolutionary advantages can become fatal liabilities under changing circumstances. The massive jaws and powerful bodies that had made Dinopithecus successful during stable climatic periods became burdensome when competing against smaller, more efficient tool users. This ancient drama between competing primates offers profound insights into the nature of survival itself. The fossil evidence from South African cave sites provides concrete proof of this evolutionary lesson about adaptability over dominance. Being the largest and most powerful primate in Africa meant nothing when environmental conditions shifted and new competitors emerged with superior technologies. This ancient lesson resonates powerfully with modern conservation challenges, where climate change and human activities threaten species that cannot adapt quickly enough to survive. Today's endangered megafauna face similar pressures that once doomed the giant baboons. The next time you encounter a modern baboon, you are witnessing the successful, smaller, more adaptable primates that survived, while their giant relatives went extinct, representing millions of years of evolutionary flexibility that their massive ancestor ultimately lacked.